Hello, this is the last lecture of the first section of our course, Cognitive Modeling. In this lecture, we are going to talk about probabilistic approaches to modeling human cognition. First, to make it clear what we mean by probabilistic approaches and why we need that, I want to start with an example. Remember the categorization example we have been talking about several times up until now, when we are hoping to build a model that simulates how humans put objects together into categories. Now look at these four examples here. We assume that at some point the model has reached a state where it has two distinct categories for tables and chairs. So the two objects on the left belong to the category table, and the two objects on the right belong to the category chair. Now, what happens if a model receives an input item like this? What do you think this is? Which category do you think this belongs to? This, I hope you agree with me, is not a very clear-cut case. So this might look kind of 65% like a chair, but also it could be used as a side table, but with less certainty. So we are now dealing with a case which can't be unambiguously and certainly be dealt with. We seem to be in a gray area. Cases like this seem like perfect examples of where a probabilistic approach seems most suitable. So the idea behind probabilistic models is to apply probability theory on our past experience, on our previous exposure to examples or to data in general. So in models like this, we usually represent the knowledge by assigning weights or confidence factors or biases to our previous observations. And then the learning mechanism has to actually incorporate these weights to come up with a way of choosing a hypothesis that explains the data the best. So often a probabilistic approach is actually relying on another formalism for representation. For example, it adds weights to a symbolic representation of knowledge. As an example, let's look at our symbolic model of representing the formation of English past tense verbs. So the idea we saw before was that we need a rule that explains you have to add a suffix to the root form of a verb in order to make it into past tense. But we do know that there are other regularities when we look at all the English past tense verbs. For example, some verbs follow this more common rule, but there are some verbs that actually don't change, like put and hit and so on. In the previous example we saw, we actually put these verbs under an exception, but we know that there's a category of verbs. They're not as common, but there are more than one example of verbs that just don't change when we use them in a past tense form. So in a probabilistic framework, you actually list all these rules, but you also add a probability value to each rule. So 70% of the times a verb is attached to a suffix d or ed in order to be used in past tense. But then 8% of the times the verb doesn't undergo any change. It is used in its root form in order to convey a past tense usage. So you see now that we have certain weights to reflect how commonly used each of these rules are, or how common or how willingly we should use each of the rules. So that's at the level of representation, seems like some sort of a weighting mechanism could help us. But then we have to decide where these weights should be and where they come from. So in other words, where do we get these probabilities? How do we estimate them? And once we have them, how do we use them in making decisions? So in this particular example, a very simple approach would be to look at the data in order to estimate the probabilities in the first place. So if you have a large collection of text in which some verbs are used in English past tense, what we can do is we can actually count the number of verbs or the ratio of the verbs or the proportion of the verbs that are used in the past tense by being added a suffix d or ed to their root form. That would tell us what the probability of the first rule is. And then if we single out the verbs that didn't undergo change, so they were used in past tense by just simply using their root form, then that will give us the probability of the second rule, and so on and so forth. Now, once we have these ways, how are we going to use them in reasoning or in decision making? So let me give you another example from a different domain. Let's look at this description. Anna is a master student in this class. She's intelligent and has a need for order and clarity. Her writing is rather dull and mechanical. She's self-centered and does not enjoy interacting with others, but she has a deep moral sense. She likes to read science fiction and play video games. If you were given this description, and then you were asked, do you think Anna is a psychology student or a computer science student? What would you say? Now, since this is an online course, I can't really listen to your answers, unfortunately. But in my experience, and this has actually been shown over and over again in experimental studies, a majority of people actually think that Anna must be a computer science student. Now, what would you say if you were given a much briefer description? So if you only knew that Anna is a master's student, what do you think would be more likely? Is Anna a psychology or a computer science student? This is a very important thing to think about, because in the previous case, when I give you a long description, you basically are trying to match this description with a stereotypical description of a, say, computer science student, as opposed to a stereotypical description of a psychology student, and you might feel that this matches the computer science stereotype better than the psychology stereotype. However, you have to also keep in mind that there are usually many more psychology students than computer science students in pretty much every university except for the technical universities. So if you didn't have any additional information, you'd be wise to guess that Anna is a psychology student just because the number of psychology students is much higher in general compared to the computer science students. So you see that we have two factors to keep in mind. One is, what is the a priori probability that Anna is a psychology or a computer science student, and what is the likelihood of Anna matching the description once we know that she comes from a particular program? So deciding what program suits better a particular case or a description of a student is actually an example of a probabilistic reasoning task. So in this case, we are given some evidence. So the box at the top is basically the evidence or observation about the characteristics of Anna. And then we have two hypotheses to choose from. One hypothesis is that Anna is a psychology student, and the second hypothesis is Anna is a computer science student. So what we need to do is to do some form of inference on observed data to infer the probability of a hypothesis. So a very common and highly widely used type of inference is called the Bayesian inference. This is called Bayesian after the well-known mathematician Bayes, who suggested a rule that's now commonly known as the Bayes rule. The idea behind this rule is if you need to make some inference and if you need certain information that's complicated, try to break it down into simpler components that are easier to estimate. So here we are talking about the probability of a hypothesis, of a given hypothesis, given some evidence. So how likely is hypothesis I given some evidence E. That's a conditional probability which we actually need in order to decide which program is more likely for Anna as a student. Now, according to the Bayes rule, we can rewrite this probability as a combination of other probabilities that are actually easier to estimate. So the first one is the likelihood that a particular type of evidence is observed if that hypothesis is true. In our example, this means how likely is it, if we knew that Anna was a computer science student, how likely would it be for her to match this description? That's, as I said, called the likelihood of evidence E, assuming the hypothesis I. But equally important is the prior probability of a hypothesis I. So how likely is I if we don't know or we don't have access to any particular evidence? How likely is it that a random student is from psychology? And then the last component is the prior probability of the evidence itself, which actually in cases where we have to choose a hypothesis, this doesn't matter because it's the same value for all of the hypotheses that we are considering. So we are going to drop this term in our future examples. So let me go back to our case at hand. We want to decide which of these two hypotheses is correct, or at least which of them is more probable, whether Anna is from a psychology program or whether she's from a computer science program. And the evidence is the description in the gray box on the right. So basically what we need for this reasoning is to come up with a way to measure which probability is higher. If the probability of psychology given this evidence is higher than the probability of computer science given this evidence, then we can say that it's more likely that Anna is a psychology student, and the other way around. But what do we need for estimating these probabilities? So as I said before, Bayes' rule tells us that in order to estimate the probability of Anna from psychology, given the evidence, we basically need two other probabilities: the likelihood of evidence, assuming that Anna is from psychology, and the prior probability of Anna being a psychology student, in the absence of any evidence in hand. So for the first probability, we basically want to go through, ideally, all of the psychology students, but that's usually difficult to do, or at least a large enough sample of the psychology students, and see how well they match this description. If a large proportion of them match this description, then we have a large likelihood probability. And if a small proportion match this description, then we have a low likelihood probability. Similarly, for the prior probability of Anna being from a psychology department, what we need to do is to look at the ratio of university students who are enrolled in the psychology program. So the combination of these two factors basically allows us to estimate the posterior or the conditional probability that we need in order to perform our reasoning. I want to give you another example in another domain so that you have a better idea of how probabilities can be useful when we make a certain decision. This is a sentence that's actually quite famous as an example of how ambiguous language can be. So the sentence goes as this: time flies like an arrow. I don't know what you understand from reading this sentence. You probably assume that it means time moves very fast as an arrow moves, which is the metaphorical sense of the sentence that's most common. However, if you think about how a speaker of English actually interprets this sentence when they hear it for the first time, you have to appreciate how difficult the task is to decide what the sentence means. Because each component in this sentence is ambiguous to a large extent. For example, the first word time can be used in several different senses. It could mean time as the fourth dimension. It could mean the verb, the act of timing someone, like time me while I'm running. Or it could refer to the well-known magazine Time, as an article was published in Time which discussed this matter. So already for the first word, we have more than one option to consider. Similarly, for the second word, we can talk about a bunch of insects, flies, or we could be talking about a verb of a bird, describing a bird soaring in the air. Or we can talk about a completely different type of flying, an aeroplane flying in the air, which is a different kind of action. So again, you see that interpreting a single word in the sentence already is a difficult task, and the combination of these two together could then also be ambiguous. For example, time flies could be a noun followed by a verb, as in time moves fast. Or it could be an adjective followed by a noun, a particular type of fly, similar to fruit flies. This can go on and on. That you can see that the ambiguity is really deep. At the level of sentence structure, there are several types of ways of parsing the sentence which is compatible with rules of grammar. I've put here two hypotheses, but there are several more. So in the first case, basically we interpret the sentence as time moves very fast as an arrow. In the second scenario, we are interpreting the sentence by saying a special kind of flies, time flies, like a specific object, in this case an arrow. So similar to the sentence, fruit flies like a banana. So how does a language user interpret this sentence and choose one hypothesis over another? If we believe that a model of language processing should take into account probabilities of each of the grammar rules and the probabilities of each of the words being used as a particular part of speech, then a model should also tell us how to combine these probabilities, how to estimate how likely it is for each hypothesis in light of all these weights that are assigned to different grammar rules and to different interpretations of individual words in the sentence. And then you can compare the likelihood, the probabilities of the hypothesis together and see whether one of them is much likelier than the other. So let me summarize the probabilistic approach to modeling cognition. There are certain advantages with this framework. First of all, probabilistic models are designed to handle noise and ambiguity. That's their strength point. That's their strong point. So they are usually very robust in cases where the data is noisy or there's a lot of ambiguity to deal with. They have become very advanced and very efficient thanks to their commercial applications. So state-of-the-art statistical techniques for probabilistic reasoning and probabilistic learning now can be applied efficiently to large amounts of data, which allows us to build cognitive models that are actually scalable and realistic in terms of the type and amount of data they can handle. They also match the probabilistic nature of humans' learning and reasoning patterns very well. It has been shown over and over again that humans are sensitive to frequencies and to statistical nature of the data that they receive. In that sense, probabilistic models match that purpose very well. They seem very suitable for building cognitive models. However, there are certain disadvantages about them. Most importantly, that the neurological plausibility of some of these techniques are questionable. It's not very clear how they can be implemented in human brain. So in these last 3 lectures, I've gone over the common frameworks for building models. We are going to see several examples, real examples of these models when we look at specific cognitive domains, most importantly domains of memory and language. So you will see real examples of these models in the future.